What's up guys, welcome back to our channel. In today's video, we're finally going to do a video on one of the most requested topics in the history of our channel, the semiconductor industry. Not only is the semiconductor industry the largest industry in all of Taiwan, but it's one of the largest and fastest growing industries in the entire world. With companies like NVIDIA, Broadcom, and TSMC all taking spots inside the top 10 most valuable companies in the world list, as well as companies like Apple, Google, Meta, Amazon, and Tesla, who all design their own chips or use chips in their finished products. As the world develops more and more advanced technology in robotics, electric vehicles, AI, smart glasses, IoT devices, and many other areas, the importance and value of the semiconductor industry will only grow, as the engine of all digital technology is the semiconductor. So there can be no doubt about the importance of this industry and the money to be made in it. But the problem is the semiconductor industry is large and complicated, and the companies in the industry are very, very specialized, making it hard for people from outside the industry or even people who work within the industry to truly understand the industry beyond their small area. I get questions all the time like, are NVIDIA and TSMC competitors? What's the difference between Broadcom and Qualcomm? And NVIDIA manufactures their chips, right? These questions all show a fundamental lack of understanding of the industry's structure. So in today's video, I'll be teaching you everything you need to know about the structure of the semiconductor industry. If you finally want to understand all of the companies in the industry and the roles they play, be sure to watch today's video. And if you want to learn more about the semiconductor industry, be sure to subscribe to our channel. Let's go. In order to understand the semiconductor industry's current structure, we need to take a look back at its history. Computers run using the binary system of zeros and ones, which represent the switching on and off of a switch. If you combine many of these switches, you enable the computer to create patterns of zeros and ones that represent actions performed by the computer. And that's how computers are able to store and manipulate information. The problem that early developers of computers ran into was that the only switches they had were vacuum tubes, which were large, bulky, and easily breakable glass tubes filled with polarized material, which allowed them to act as switches, which could be turned on and off. These were used to represent the binary code of a computer. At that time, computers were huge, unreliable, and very, very slow, as electrical energy had to flow through the entire system of vacuum tubes for the computer to work. So in the 1940s and 50s, as a way to advance computing capabilities within a smaller space, semiconductors were invented, which used silicon, a semiconductor material, along with other polarized and non-polarized materials on top of and within the silicon to allow for the control of electrical energy across the chip. Then transistors, the actual switches, were placed on or carved within the silicon, allowing the chip to act as the on-off mechanism that a computer needs to function. Early semiconductors were much smaller, faster, more durable, and powerful than vacuum tubes. Throughout the 1950s to the 1970s, semiconductors were developed and advanced rapidly by computer companies like IBM and Apple, and early chip companies like Intel and Texas Instruments, who not only designed but also manufactured and assembled their own semiconductors, while also designing the machinery and software used to make these chips. This model is known as the Integrated Device Manufacturer, or IDM model. But these early semiconductor companies ran into a huge problem. They were pressured by two seemingly opposing forces which guided their research and development. First, customers wanted smaller computers, and second, customers wanted more powerful computers. The only way to make this possible would be to fit more resistors onto a single chip and at the same time make the chips smaller. This would allow for computers to be smaller and more powerful than ever. This concept became the guiding principle of the semiconductor industry, Moore's Law, which says that resistor density should double every 2 years, allowing for the exponential growth in the power of computers. But in order to keep up with Moore's Law and the demands of consumers, early semiconductor companies had to continually develop more and more advanced ways to make computer chips smaller and more powerful. By the 1980s, it became clear that in order to develop advanced chips fast enough, the semiconductor industry would need to become more specialized. One company can't do everything and move fast. So in 1987, a 55-year-old Chinese-born American seized on the opportunity to completely revolutionize the structure of the semiconductor industry. His name was Morris Chang, and the company he founded was called TSMC, which became the world's first pure-play foundry, or a company that only specializes in manufacturing other companies' chips, but does not design or sell their own chips. This marked the beginning of the end of the semiconductor conglomerates like Intel and Texas Instruments, as in response to TSMC now designing chips for clients, companies no longer needed the billions of dollars to design their own fabs. They could simply design their own chips and have TSMC handle the manufacturing. This process led to the highly specialized industry that exists today. The current semiconductor industry is made up of many different types of companies that contribute to the supply chain and make it possible for semiconductors to continually keep pace with Moore's Law. Here are the main categories of the semiconductor industry companies. First, we will start with the design categories. Then we will move to manufacturing categories and then to the companies who do both. Remember, the structure of these companies is very complicated, so many companies often fall under multiple categories. For example, Samsung is the world's only company that could reasonably fall within every single one of these categories, as Samsung has both a foundry, a chip design, an OEM business, component manufacturing business, a machine tooling business, and every single other thing in between. The first part of the semiconductor industry, which was enabled by TSMC's innovation as a pure-play foundry, is the design section, specifically Fabless-chip design companies. These companies design chips using EDA, or electronic design automation tools. That means they create the chip design down to the transistors and the architecture of the entire chip system. Sometimes they design chips, sometimes they design an entire chip system called an SoC, which contains many different types of specialized chips connected together on a single board. But crucially, these companies are called fabless because they do not own a semiconductor fab, meaning they simply do design and do not manufacture any of their designs. They simply design the chips and then send the design to the foundry for manufacturing. They also contract all of the suppliers for all of the components needed to build the devices and provide guidance on how their chipsets should be assembled and tested. The biggest fabless chip design companies are NVIDIA, who makes GPUs for AI and graphics, Broadcom, who makes chips for data centers, wireless communication, and networking, AMD, who designs GPUs and CPUs for PCs and data centers, Qualcomm, who designs SoCs and modems for mobile devices like smartphones, PCs, and VR, AR devices, and MediaTek, who also designs chips for mobile devices. The next section of the industry is called fabless non-chip design companies. These companies also design their own chips, but unlike the fabless chip companies, designing chips is not the main part of their business. Generally, the main part of their business is in another related industry, like software or consumer technology. But they design chips to support that technology. They then send their designs to the foundry for the chip manufacturing, just like the fabless chip design companies. The top companies in this area include Google, Amazon, Meta, Tesla, and Apple. The third type of company in the design phase is IP and EDA companies. These companies design the complex software, known as EDA, which is needed to design chips. They then license this software to chip design companies who use it to design their chips. The largest companies in this area are ARM, Synopsys, and Cadence. If you're watching this video, I'm sure that must mean that you're really interested in the semiconductor industry. Maybe you're an engineer already working in the industry, or you're an international student preparing to enter the US job market. Honestly, I've always believed that Taiwanese engineers have incredible global talent, and people like this are exactly what the US tech sector needs. I remember when my wife, Wei Ling, applied for jobs using her education and work experience from Taiwan. From sending out her resume to getting her first job off, it took her only a month and a half. She actually landed a job at a top US fabless chip design company before I did, and I'm a US citizen. The job market now is tougher than ever. Taiwanese interviewees face intense competition and very difficult interviews, while also trying to navigate the huge cultural differences between US and Taiwanese companies. That's why I'm really grateful that Wei Ling had the help of Qing Xue, a US semiconductor industry career coach. With Qing's guidance, Wei Ling was able to land her dream job in the US semiconductor industry with a 3x salary increase over her job in Taiwan. Qing used to be an engineer at TSMC, then successfully transitioned to Samsung and AMD. She's now turned her 12 years of industry experience into a complete online program called G.R.O.W, International Career Development Masterclass. It's an 8-week practical course that walks you through everything from clarifying your career direction, to using AI to craft a personalized resume, to preparing for English interviews, or writing follow-up emails, and to mastering salary negotiation. This system not only helped Wei Ling find her dream job, but I also believe that it can help you find your dream job as well, especially if you're looking to break into the US semiconductor industry. If you're feeling lost about your career lately, I highly recommend booking a free career consultation with Qing. She'll help you identify the key points in your job search and get you on the path to finding a better career. The link to her website is in the description below. Be sure to check it out. After design, the next section of the industry is called manufacturing. And the first company type under the manufacturing section is foundries. These are companies who specialize 100% in the manufacture of chips, not in the design at all. They handle the chip manufacturing process from receiving the designs from the design company to creating a finished wafer, which contains hundreds to thousands of chips. The manufacturing process for advanced logic chips is the most technically complicated and intensive process in the world. It includes dozens of steps, highly specialized manufacturing tools, and billions of dollars for facilities, equipment, and materials. Because it is so technically complicated and expensive to become a foundry, very few companies can do it well. It is also becoming more difficult and more expensive to manufacture the most advanced chips, which is why TSMC has virtually become the world's only source of advanced semiconductor fabrication. This is also why so many modern chip companies choose to be fabless. It's much cheaper and much more efficient that way. The main benefit companies like TSMC have as pure play foundries, which means they only manufacture chips for clients and don't manufacture chips based on their own design, is that clients can trust TSMC will not try to copy their design and directly compete with them. This trust has allowed TSMC to manufacture chips for all of the top chip design companies like NVIDIA, Qualcomm, Apple, Broadcom, and MediaTek. And at the same time, TSMC is also able to differentiate itself from its competition like Intel and Samsung, who are not pure play foundries. This also allows TSMC to manufacture at a scale that no other company can imagine, because they're basically combining the demand from all of the fabless companies all into one. So they're able to basically do things at such a higher scale that they can divide the extremely expensive fixed costs in the industry across a huge demand, lowering their per unit costs and making them basically untouchable by their competitors. Other foundries include Samsung, Intel, Global Foundries, UMC, and SMIC. There are also foundries who specialize in making non-logic chips, or the chips that are used for functions other than being a processor of a device, like memory or analog chips. These companies are not pure play foundries, and so will be discussed later in a section called IDMs. The next section under the manufacturing part of the industry is equipment manufacturers. Equipment manufacturers are the companies that build equipment used to manufacture and assemble semiconductors. These are mostly very advanced machines like crystal growth furnaces and wafer slicing and polishing tools for making silicon wafers, EUV photoresist and etching equipment used for fabrication, defect inspection systems used to test the finished wafers, and assembly equipment like wafer slicing saws, wire bonding machines, and final testing systems used to assemble and test the finished chips. Some of the biggest semiconductor equipment manufacturers include ASML, Applied Materials, Lam Research, Tokyo Electron, and KLA. The next section under the manufacturing portion of the industry is component manufacturing. These components include passive components, memory, PCB and substrates, communication components, and sensors. Basically all of the things that go into a chipset that are not actual advanced chips. Passive components are electrical devices used in a chip system that do not produce energy but help regulate it, like capacitors, inductors, and resistors. Memory is the type of chip designed for storing digital information. These are essential for computers to be able to save, reference, and recall previously processed data. PCB and substrates are the physical boards that a chip device is mounted on. They house the chips, passive components, and wiring that connect a chip system. Communication components are things like RF modules and antennas that allow the chip system to send and receive wireless signals. And sensors are a part of the chip system that allow it to absorb information from the surrounding environment. These include image sensors, microphones, and touch sensors. The main component suppliers in the industry are Murata, TDK, Taiyo Yuden, and Samsung for passive components, Micron, SK Hynix, and Samsung for memory components, Ibiden and Unimicron for substrates and PCB, Qualcomm, Murata, and Broadcom for communication components, and TDK, Samsung, and Sony for sensors. The next type of company under the manufacturing section of the industry is OSATs, or Outsourced Semiconductor Assembly and Testing Companies. OSAT companies have a central role in putting together the finished chipset. Remember, the fabless chip design company simply creates the design, and the foundry manufactures the advanced chips, and the memory chip supplier manufactures the memory chips, and the passive component suppliers manufacture all the other parts. But someone has to actually take all of these separate pieces from all these separate suppliers and put them together, and that's what the OSAT does. Once these devices are assembled together by the OSAT, they are then tested to make sure they meet the specifications of the design company, and then the OSAT sends the finished chipsets back to the fabless design company or onto the end device manufacturer. Some of the largest OSAT companies are ASE, Amkor, and JSAT. The next section of the semiconductor industry is called design and manufacturing, and under this is the IDMs. IDMs, or integrated device manufacturers, are companies who do both chip design and chip manufacturing, as well as assembly and testing of their own finished chipsets. This is the model followed by the original computer chip companies like Intel. They essentially create their own design, buy the components from the component suppliers, fabricate their own chips, and then assemble and test their finished chipsets. There are two main problems with this model, especially for making logic chips. One, it is extremely hard to compete well at everything. The specialized nature of the industry means most companies focus on one area and do it very well. So an IDM really struggles to have the resources to focus to compete at all levels. And number two, the IDM cannot compete well as a fab because fabless chip companies prefer to use a pure play foundry for their fabrication because the pure play foundry isn't their direct competitor. For example, AMD might design a PC chip. It can either choose to have the chip manufactured by TSMC, which is a pure play foundry, or Samsung or Intel, who are IDMs who compete in the PC chip design business with AMD. AMD will almost certainly choose TSMC because there's no worry that TSMC will copy their design to make their own PC chip to compete with them. The main logic chip IDMs are Intel and Samsung. There are also many IDMs who create non-logic chips, as the IDM model is a much better fit for less advanced non-logic chips, like analog, memory, and power semiconductors. Some of the biggest non-logic chip IDMs include Micron, Texas Instruments, Analog Devices, SK Hynix, and Infineon. And the final section of the semiconductor industry is the OEM, or the original equipment manufacturer. These are the companies who make the end products that use semiconductors in them, like PCs, phones, IoT devices, cars, and data centers. Some of these companies design their own chips like Tesla, Apple, and Amazon, while others buy chipsets directly from a chip design company like GM and BMW, who buy their auto chips from Qualcomm, or Oracle, who buys their data center chips from NVIDIA and AMD. OEMs are perhaps the largest group of companies because this group contains all companies who make any kind of electronic device. The largest OEMs in the world include Meta, Amazon, Google, GM, Tesla, Apple, Samsung, Lenovo, HP, and many others. So now that we've outlined the entire industry structure and how all the different companies work together to build finished chips, let's go through what the process of making a finished chipset actually looks like in reality. In this example, we'll use a chipset for a smartphone. The smartphone OEM, let's say Samsung, needs an SoC for their Galaxy phone. First, they have to decide if they will design the chip themselves, making them take on the role of the fabless design company, or if they will remain just as an OEM and order the chipset from a fabless design company, let's say MediaTek. In this instance, Samsung decides to pay MediaTek to design the SoC for them. So MediaTek, as the fabless chip design company, is now responsible for making the design and getting a manufactured and assembled chip back to Samsung. So next, MediaTek makes the design and gets a list of all of the components and suppliers needed for the design. This includes which fab will manufacture their logic chips, the GPUs and CPUs, let's say they choose TSMC, which IDM will supply their memory chip, let's say they choose Micron, and which suppliers will provide their passive components, let's say Murata, and which suppliers will provide PCB and substrates, let's say Samsung, which supplier will provide communication components, let's say Murata, and which supplier will supply the sensors, let's say Sony. MediaTek will then place orders with each of the suppliers they choose for all of these parts. TSMC will then produce the logic chips according to MediaTek's design, using advanced equipment from equipment manufacturers like ASML and Applied Materials. Then once all of these parts are manufactured by each supplier, they will be sent to an OSAT that MediaTek chooses. Let's say they choose ASE. ASE will then receive all of the components that MediaTek has purchased along with a build plan, which instructs ASE how MediaTek would like their chipsets to be assembled. ASE then assembles the chipset and tests it to make sure that it works according to MediaTek's designs. Once the chipsets are approved, they will then be sent back to MediaTek and then ultimately sent on to the final customer, Samsung. Or they will be sent directly from ASE to Samsung. Samsung then takes the finished chipset that MediaTek creates, puts it in their Galaxy phones, makes sure it works, and then sells the phones to consumers. So that's it for today's video. I hope you've developed a better understanding of the semiconductor industry structure and how all of the companies work together to make finished chipsets. If you have any questions or comments, or you want to learn more, please be sure to leave a comment below. And if you want to learn more about the semiconductor industry, be sure to subscribe to our channel. See you next time. Bye-bye.